Okay, students, let us start question number 5 from your practical list. So question number 5 says, write an assembly language program to simulate the following logical operations on two user-entered numbers. So you have done all these instructions earlier in your lab periods, and we have written a assembly language program to simulate all these operations in the lab. I'll be recounting it for you. Let us see. So please see, what we are doing this time is we are taking two variables, let's call them A and B, and declaring as we had declared sum and diff variables in question number 3 and question number 4 respectively in the lab classes, and the videos of question number 3, question number 4 have already been shared with you. So what we do is we read two numbers. The first number we read and we store it into A. So what happens is when I say read, a number is read into AC. I'll show you how this will execute. So I'll say, see, I've already done these instructions. So I'll simply step instruction by instruction to show you how this will work. So I'll say read oh. Let's stop, reset everything, and assemble and load. And now let's start, okay? Let's say I enter the first integer as 4. You can see 4, the AC now contains 4 after the read instruction. I want to store this value of AC at A. So A is here at address 34, right? Now A contains 4. Read next number. Let's say I put in 7, okay? So this number 7 is now in AC. And after I say store B, it comes to be stored in this location with address 36 allocated to the variable B. Okay. Now, what we do for any of these operations like AND, OR, XOR, NOR, NAND, for any of these operations that require two operands, what we do is we load the first operand into A, and then we, let's say if we want to AND, then we AND it with B, okay? So when I say load A, what happens? A gets loaded in AC, right? You can see that A gets loaded in AC, and now I will AND it with B, okay? Now, when I say AND it with B, please see what should happen. I'm converting this value to binary so that you can see what should be the result. So you are seeing that this is A and this is B. What should be the result of their AND? The result of their AND should be tetra 4, tetra 4, tetra 4, then 0, 1, 0, right? That is 4. So after this AND operation, AC should contain 4. Okay. So let's do this and see the AC contains 4 now. And we'll say write, and the output is 4. Okay. Similarly, when I have to OR these two numbers, I'll again load A into AC. Okay. And then I'll OR it with B. Now what should be the result? Please see. When I'm ORing these two numbers, tetra 4, tetra 4, tetra 4, 0, 111. So this time the result should be 7 in AC. Okay, right now it is 4. After we do this, if the instruction is executed properly, the result should be 7, right? You can see the result is 7 in AC, right? And then we say write, and the output is written. Okay. Now, so if we had to perform XOR or NOR or NAND, so similarly, we would have done what? We would have simply said load A and then NAND B or NOR B or XOR B and then write. Okay. Let's look at the NOT operation. Okay, this NOT operation. Now, since if we have to do a unitary NOR, that means if it is a operating on a single operand, then what we do is we simply, let's say, we first load A into AC, and then we can simply say complement A, right? This will be NOT of A, okay? And we can say write. So you can see now I have loaded A, right, in AC, converting this to binary, okay? And then I say CMA. So you can see that all the entire value in AC is now complemented. That means we have obtained the NOT of AC, right? And whatever the decimal number of this value is, it is written as output. Okay. Similarly, we do with B. Okay. And right. Is this clear? Right. So this is question number 5. Let us look at question number 6 next. So question number 6 says write an assembly language program for simulating the following memory reference instructions, that is add, LDA, STA, BUN, and ISZ. So we have already done add. I have already explained add, LDA, STA in the question number 3 and question number 4. Okay, so so you can see that I'm simply writing, I've simply used the same add instruction. Here we had made this instruction add, you remember? Right? What we were doing is how we were implementing the add machine instruction. We were first, since add and see, all of them are going to be similar. Okay, add. So let me cover all these instructions with you once again. Add, and, or, XOR, NOR, all these instruction, all of these are what? These are memory reference instructions. So all of them will have to contain the fields OP and ADDR, right? The first four bits of these instructions will specify the opcode, and the rest will specify a 12-bit address, right? We know that as opposed to this, the register reference instruction or the IO instruction formats, the entire 16 bits can be used for the instructions. So we have made another opcode, okay, that we called opcode 2 of 16 bits for these instructions. So this is the opcode 2 that we had made, right? Now, for the memory reference instructions, we are using the fields OP and ADDR as I had explained to you earlier and made them both required. Okay. Now, the first thing that we do is we transfer before the implementation of any instruction starts, we know that the fetch phase has already placed the instruction into the instruction register. So we transfer the address part of that instruction register, which is stored in the bits 4 to 15 into the address register, into the memory address register called MAR. We go to the main memory at that address and transfer the contents into the memory data register. And then whatever is to be done, if the operation is add, we say AC plus MDR and the destination, and the sum goes to the destination AC again. If it was subtract, please see the entire thing is same, only this micro instruction changes. So which can be made from here. So the only changes that I select either add or subtract or multiply or divide if it is a arithmetic, instruction. Okay, if it is a arithmetic instruction. If it is and or not, that is logical, then we choose the logical instruction from here, and we just differ. You can see the entire thing is the same. That means the source 1 is AC, the source 2 is MDR, in which we have placed the operand, and the destination of the operation should be AC again. And what do we want to do? We either want to do and, or we want to do or we want to do NAND or NOR or XOR. Okay, we just have to select this. Of course, CPU sim will do the operation accordingly, right? So this micro operation, that is either arithmetic or logical or shift, this can be selected from this drop down menu on this dialog box itself, or we can choose it from the micros. You can see I could have gone here for the arithmetic instructions and said new. So the same dialog box opens, and from here I can branch over to the logical instructions, or I could have gone to the logical micros here and opened this, and gone to the arithmetic instructions from here. Okay, so this is how we make add and so that you can see that all the instructions are same except for this, whatever operation is to be done. Is this clear? For or, this will again change, it will become or. Is this clear? Right. So this is how these instructions have to be executed. So what I've done in this program is I have just forget this for a minute. Okay. Now I have just put add, and you remember we had used add sum. I'll show you. See, add sum in our earlier programs, and here I'm saying add 14. Okay, so why? Because sum is what? Sum is actually the name given to a particular address. Okay, when I say sum, we have seen that the system gives a particular address. This value allocates 2 bytes to it and gives it this name. Okay, so whether I write sum or I write an address here directly, it is just one and the same. So purposely, I have put directly the address here. Okay, so now when I say add 14, I'll show you how this will be executed. Let's see this program instruction by instruction. Okay, so let me put in something here at address 14 to be added to AC. So after this is added to AC, the contents in AC should be tetra 0, tetra 0, tetra 0, triple 1, right? So let's say step by instruction, and you can see that the result is tetra 0, tetra 0, tetra 0, tetra 1 as we had expected, and we'll say right. So it should write 15 here now, right? So tetra 1 is 15, right? So after this, what we are doing is I'm demonstrating the LDA instruction once again. So we have already done this in question number 3 and 4. I'm just illustrating these here. Okay, so LDA will do what? Whatever is stored at this location 16, it will be loaded into AC. Okay, and as I told you, the name of LDA in my machine is load. Okay, so I go to this address 16 and I put this, let's say value 1011 here, which is 13. Okay, so let's say step by instruction, and you can see that in the AC, the value 13 is loaded. Okay, and then we write, so, oh, 13, I'm sorry, the value 11. This is 11, 1011 is 11. So 11 is loaded and it is written. Now, we are demonstrating the STA, okay, STA instruction. Again, this was implemented, its implementation was shown to you in the previous questions. I'm executing it now. So whatever is right now, the value in AC should get stored at address number 18, right? So let us see what is the value at 18. It is 0 right now. So when I say step by instruction, please see at 18, the value of AC, that is tetra 0, tetra 0, tetra 0, 1011, which is decimal 11 is stored. Okay. And now finally, the instruction bun. Now what does it do? Please see. What does this instruction bun do? So bun, as I've explained to you in the class, it is a memory reference instruction which will simply transfer the control of the program to the said address. So which means that if I have said bun 10, so it should transfer the control back here. That means the value of PC should become 10. Okay, after this, the value of PC, after I execute this, the value of PC should become 10. By chance, it is already 10, but in any case, even after the execution of this program, otherwise it should have become 12. Now, let us step by instruction, okay, and see the value of PC. So you see that every time PC is incremented by 2 in my machine, right? But this time the PC is not incremented by 2. Rather, you can see it has gone back to this instruction 10. Is this clear? Right. So how to implement this bun? This is a new instruction for you. I'll show you. So you can see the bun instruction is one of the simplest instructions. What do we do? As usual, we transfer the address part of the instruction register to the MAR. And what do we want to do now? This time, when I'm saying bun 10, I just want to transfer my control to this address 10. That means the next instruction to be executed should be the one which is placed at the address 10. That means please put this address 10 in PC. And we have put this address where? From the instruction register, we've put this address into the MAR right now. So what we will do is we will simply say that please put MAR into PC. And what kind of a transfer would this be? This would be a register to register transfer. So simply you can see that the source is MAR and the destination is PC. The start bits of both are 0 and all 12 bits are to be transferred. Okay, so this is the bun instruction. Now there is another instruction here in the next question that I want you to see, which is, let's see question number 7 as well. So in the question number 7, you've done all these instructions in your lab classes, right? So I'll skip these for the moment. I'll show you the instruction increment next. Okay, how to what does this mean? So as explained in the classes, increment simply means what? Increment simply means increment the value of AC by 1 and put the same back in the AC. Okay. So how to make this instruction? Let's see. So let's say modify. What do we have to do? We'll simply go to the increment micro and I have made this instruction. You can see I've named it increment AC. So what do we have to do? We just have to select the register which is to be incremented, which will be AC in this case. Okay, and by how much it is to be incremented? By default, it is to be incremented by 1. And if there is an overflow, then as usual, the halt bit that we made, you remember, the halt bit was the 0th bit in the status register that we had made. Okay, we set that bit. Okay, so that the program, if there is an overflow, the program execution can be gracefully stopped. Okay, so I'll say okay. And this is the only, you can see that this is the only instruction which is put here, and then end. Okay, so what will this do? This will simply increment the value of AC. Clear? Now there are two other machine instructions that I want you to see. They are circular right and circular left. Let me give you the context for these. So we've already seen the shift instructions in our class. I'm just recapping it for you. So the shift instructions could be logical shift instructions. They could be circular shift instructions. There are also arithmetic shift instructions. They are not in your course. So I'll explain the logical and the circular shift instructions. So let's say if we had a 4-bit accumulator register, that means if the total width of AC was, let's say, 4, and it contained the value 0100, that is in decimal 4. Okay. Now, if I left shifted the AC, okay, if I left shifted the AC, then what would have happened? This is the logical shift that we are talking about. So we are talking about logical left shift. Okay, if I logically left shifted AC, then all these bits would have moved 1 bit to the left. Okay, so this bit, the leftmost bit, this would fall off. In its place would come 1, followed by 0, followed by this 0, and this bit would become empty, right? Then this bit is automatically padded by a 0. So as a result, we get 1000. Okay. In decimal, this is represented by 8. So whenever we do a logical left shift, it is always equal to multiplying the number by 2. It is always equal to multiplying the existing number in the register by 2. Okay, let's look at the logical right shift. So in this case, again, we are assuming AC of 4 bits, which contains the initial value as 1000, which is the binary equivalent of decimal 8. Now, if I right shift this by 1 position, then this rightmost bit will fall off. Okay, and all these bits will be shifted 1 place right. As a result, the leftmost position now will become empty, which will be filled by default by 0. Okay, so after the right shift, we will have 0100, which is equivalent of decimal 4. So every time you do a logical right shift, it is equivalent of dividing a number by 2. Okay. Now let us look at the circular right shift and circular left shift. Now in the circular right shift, please see, we shift the numbers that by 1 bit as usual. If it is a right shift, 1 bit to the right. The only difference is that the rightmost bit, when it is now circulated, when it is now shifted, it gets circulated, it doesn't fall down. Instead, it gets circulated and comes to the most significant position. Okay, so as a result, we will have what? We will have the result as 0010. When I do circular left shift, the leftmost bit will also not fall down. It will get circulated and come and occupy the least significant bit position. So the answer would be 1000. Okay, so after the circular right shift and left shift, the resultant value in the register would be 1000. Okay, so how to do this? It's very simple, really. So I'll simply go say modify machine instruction, and please see there are shift instructions here. You can see that. So I'll say this and new, and then I've already made the CIL. So we say CIL. What register is to be shifted? It is the accumulator, and then the result is to be put in which register? It is in the accumulator. And what type of shift do you want? We want the cyclic shift. And what is the direction? We can say left or right according to the type of instruction that we are making. And how many bits do you want each bit to be shifted? We want them to be shifted by 1 bit each. Is this clear? So this is all we have to do, and we'll say okay, and then we can say CIL here. Okay, that's it. So we have already covered. We have covered question number 5, 6, 7, 8, and up to question number 9 we have covered.